Hi everyone, my name is Hexin. I'm a PhD student at Department of Microsystems, University of South-Eastern Norway. I'm currently working on Apple's project User Case 2. Today, I'm going to present my recently published work related to the Apple's project. The title of the paper is Evaluation of Silicon Diaphragms for Hermetic Packaging of Microbolometer Arrays. I will start with a brief introduction before going into the results of the study. Nowadays, uncooled infrared thermal cameras have a wide range of applications. The core detector of this type of uncooled infrared thermal cameras is a microbolometer. To ensure necessary performance, they are encapsulated inside a vacuum atmosphere by bonding a micro-machined diaphragm to the device. The diaphragm covering the vacuum cavity will deflect due to the pressure difference between the surrounding atmosphere and the low-pressure atmosphere inside packaging. Thin diaphragms is able to provide low-loss transmission of infrared light, which is critical for the operation of microbolometer arrays. However, thinner diaphragm gives larger deflection, which may influence the infrared light transmission and thus affect the performance of microbolometers. If the thickness of the diaphragm is too thin, fracture may occur. In our study, we used the simulation software console for detecting the maximum allowed deformation and stress of the thin diaphragm. A 3D model of a square diaphragm was built in console, where the cavity was set to a high vacuum. The outer pressure was 1 atm. The thickness of the diaphragm was varied in the range of 60 to 300 micrometer. These simulations was repeated for different diaphragm surface areas. Single crystal silicon was selected as the diaphragm material since it is transparent to the infrared light. Besides, ring tracing software Dmax was used for evaluating the effect of a deformed diaphragm on the infrared light transmission. Figure 3 shows the layout of the optical design. A lens is required to focus the infrared light on the microbolometer sensor. The deflection of the diaphragm is based on the deformation results obtained from the console simulations. The console simulation results are shown in the Figure 4. Figure 4a shows the maximum displacement. Figure 4b shows the maximum first principle stress with diaphragm thicknesses varied from 60 micrometer to 300 micrometer and with different diaphragm surface area under the differential pressure load of 1 atm. From Figure 4a, we can see that the deflection increases with an increase in surface area of the cavity, and the difference is more pronounced as the cap thickness decreases. The maximum displacement and the associated stress of the diaphragms start to saturate for the diaphragm thickness values higher than 200 micrometer. Figure 5 presents the top view of first principle stress distribution and the cross-sectional view with a surface area of 10 times 10 mm square at a diaphragm thickness of 200 micrometer and 60 micrometer. Figure 5a and c shows there's no change in first principle stress distribution when changing the thickness of the diaphragm. Figure 5b and d shows that the maximum stress is concentrated at the edge of the silicon diaphragm when the thickness of the diaphragm with surface area of 10 times 10 mm square decreases from 200 micrometer to 60 micrometer. A noticeable deflection due to pressure difference is observed. Response diagrams was calculated in Dmax to give indication of the image quality of a point per object. The location where the infrared light will focus on the microbolometer sensor is given by the IMA. Figure 6 shows the image surface spot diagram of the diaphragm before and after deflection. As seen in the figure 6, after bending, the MMA slightly change under different incident angles. The MMA at the center remain unchanged. So our main conclusions. We found that a single crystal silicon diaphragm with a surface area of 10 times 10 mm square should have a thickness above 70 micrometer, and for a 12 times 12 mm square surface area, the diaphragm should be thicker than 90 micrometer to prevent mechanical failure. As for optical performance, our study shows that the microbolometer performance will not be affected by the diaphragm thickness in the range of 60 to 300 micrometer. But our simulations are performed in an ideal setting and does not consider properties such as surface roughness of the diaphragm due to etching, which could result in a considerable loss of the infrared signal. In the case of the wafer-level packaging, the dicing will occur after packaging and could potentially cause diaphragm failure if the diaphragm is too thin, so even thicker diaphragms can be considered. The full paper has been published in 2020 ESTC conference. The DOI link as seen in the slides. Here shows the partners involved in the Upload project's user case 2. Thanks for listening.